That thought just came to my mind because I know one professor here in Finland, a Finnish professor who works at the moment with Roger Penrose and Stuart Hameroff. And I was just thinking quietly that would it be possible to ask via those persons? And I don't know.
Yeah, I think we can try, and that's nice thought, but at first we need to get the basic understanding for ourselves, and afterwards we should.
Yeah, we would benefit more.
Yeah.
When we are qualified enough to ask good questions, that might be a good idea.
Yeah. So let's start, and we finished our previous call at the subchapter 6. So, and that chapter is about like different operations applied to the differential forms, like with scalars, vectors, and other. And first one is combining one form with a vector field to give a scalar field, and it's depicted on the figure 38 here. So here you can see.
Oh, Slava. Yeah. I don't think you're sharing your screen.
Yeah, I forgot to share. Yeah, sorry. And I need to share not my screen, but the browser window probably, because you will not see the mouse. So do you see the mouse pointer on the figure 38?
Yeah, I can see it.
Yes.
Great. So that's like the first operation, combining one form with vector field. And you can see that to combine those, we just need to count number of the surfaces the vector is piercing. So we have a -5 here because the direction of the form is like orientation of the form is in the opposite direction of the vector here. So vector kind of acts in the opposite direction. Yeah, also we can have like vectors acting on a scalar field, and vector acting on a scalar field give us a new scalar field, and this is given by contracting the exterior derivative of the scalar field with the vector. So basically we are taking the exterior derivative of a scalar field, obtain one form, and then just converge or how to say collapse the vector field with the one form as in the figure 38. And one more thing described here is the internal contractions, and actually like the usual name for that is the interior product. And in the terms of pictures, what's going on here is that if we have a P form and a vector field, we can obtain from it P-1 form. And in algebraical terms, it basically means that we just substituting feeding the vector field into the first argument of the P form, which kind of needs P vectors to be fed inside algebraically. But from geometrical perspective, what's going on here is depicted on figure 39. And in that case, you can see that we have two form, which is right here, just red line, and blue vector. And to have the internal contraction, we just need to swipe that form along the vector and basically obtain the surface here. So, and surface is the one form. So we are obtaining the green form from the red one by internal product of it with the blue vector here. And that's how those things are described geometrically. I think that's interesting theme, and maybe like as bonus task for you is to go and search some information about interior product, because interior product is pretty important thing, and it's also important because we can describe using that what is called like Cartan magic formula, or Cartan formula or Cartan homotopy formula, we can describe the Lie derivative, which we have seen in previous chapters, using the anti-commutator of the exterior derivative and interior product. And it is described in those ways. So I don't have like the nice geometrical picture for you to explain that formula today, but that's like an exercise for everyone here, and I think that we will think more about that when we will encounter the Lie derivatives again somewhere in the next chapters, for example. Yeah, and now we can go to the metric chapter, which describes basically metrics. And here we can also see that if you have standard Euclidean space, usually we can think about the matrix like something which gives us a chance to measure lengths and angles. And basically we can think about the surfaces of the same, of the equidistant points from one selected point as sphere or ellipsoids here. So basically those ellipsoids, they are exactly the matrix form, and by that I mean, the standard thing is standard Pythagorean theorem, like x squared plus y squared equals 1, and we have a circle, right? And in 3 space we will have a sphere, etc., and also higher dimensional spheres. But if you will have other form of the matrix, you will obtain maybe some shifted spheres or some compressed ones, like 2x squared plus 8y squared equals 1, and therefore you will be obtaining some kind of the ellipses. And on figure 40 we have representations of those ellipses at different points, yeah, as far as I understand, I don't remember exactly. Let's take a look at the text here. Yeah, so he's saying that if metric is flat, as in figure 40a, we will have the same matrix everywhere, and if metric is not flat, then those ellipsoids will be will have different form at the different points, and you can see that on the picture B here. So basically the curvature is manifesting in those pictures as dynamics in the metric surfaces there. Yeah, and on the picture 41 here we have the space-time matrix, which we have seen in the special relativity theory, and basically equidistant surfaces will depend and have different forms for different vectors. So to measure time-like vectors, you are using the picture A, the two-sheet hyperboloid here, and those surfaces will be concentric one, so for different vectors lengths. And at the limit where you have a speed of light or photons flying, you will have the familiar cones shapes. And for space-like vectors, we will have the one-sheet hyperboloid, or if you will use two space, you'll have just a hyperbola, but vertical one. And that's the basic form. So, and to calculate the length of the vector, we need to draw those concentric ellipses at the point, and afterwards just count where the vector ends. And here we can see that the vector has length 2. So basically, matrix is the filling of the space with that concentric map of the surfaces to measure lengths. Yeah, and here we on the right on the figure 43 we see how to measure the length in the basically Minkowski space. So we have all of those hyperbolas and those lines here, and in that space you can see that we'll have like different lengths measured by the hyperbolas. Yeah, and the next theme is orthogonal subspace and how to find those. And that's depicted on the figure 44 here. So using the metric ellipsoid, we can prescribe the orthogonal space, red here, to a vector blue. And the orthogonal space is tangential to the ellipsoid. So basically we just kind of draw the vector, have ellipsoid, and just put a tangential space to it. And that will be orthogonal subspace for our selected vector here. And on figure 45 we see how to do that in the Minkowski space. So in that case the tangential lines will go through the point on the hyperbola here. And on figures 46
excuse me?
Yeah.
Can I ask one thing here?
Mm-hmm.
I'm a little bit confused because it says the orthogonal space. Is it really the red line? Is this the space, or is it the divider of the space? How one should think about it?
We have two-dimensional space, so it's the orthogonal subspace, like the whole one. So like in 2D we can have only like two lines, right? So one line is spanned by the blue vector here, and the other line is spanned by the red one. So, and those two 1D spaces in product will give us the original one.
All right.
And for 3D space you will have a plane here, and instead of the ellipses in the plane you will have ellipsoidal shape in 3D. And tangent space to it will be a plane instead of the line.
Yeah, I understand.
Yeah, so, and like in full-blown space-time you will have like a three-dimensional hyperboloid in 4 dimensions, and you will have three-dimensional tangential space to it here. So to the vector, that red line will be the whole-blown three-dimensional space. Yeah, but like for basic calculations, you know, like the standard space-time diagrams, which are usually drawn in 2 dimensions, that mechanism is kind of good enough to draw like perpendiculars in Minkowski space, basically. And it reminds me about like Lorentz transformations. I think that's like a scissor transformation we have seen in Chris's videos. And that's basically done like that. So I think that's the Lorentzian transformation here, what we see. That's it.
So I have a question about the orthogonality. So is it that the interior product of the like blue line and the red line, that would be 0? What about these two makes it orthogonal?
But probably not the interior product, because I think that interior product in that case will give us like the whole space actually, because if you will drag the red line over that blue vector, you will have a whole plane. So not interior product, but maybe you wanted to say like a scalar product of 2 directions there, then yes.
Yeah, exactly. So I'm just wondering, are like in figure 44, are these lines supposed to be perpendicular to each other? Is that what we mean by the orthogonal space?
Yep. So like the surfaces of the equidistant surfaces of the matrix, those ellipses, and the tangents to those surfaces, they will determine the directions which are perpendicular, and in this case it means that if you substitute the vector pointing over that red line into matrix and the vector depicted as the blue one here, you'll obtain 0. So basically, yeah, that means that scalar product of those two vectors, like red one and blue one, will be equal to 0.
I see. Okay, thanks.
Yeah, and in the same way, like if you will go to the cone shape here in the Minkowski diagram, then you will obtain like self-perpendicularity. So basically, for the cone, the tangential vector will be the same line, and you will have the case when you have like self-scalar product of the vector equals 0, and that's the way geometry works in the Minkowski space. Yeah, so the next thing is measuring angles, and like I'm not sure that I really understand that well, but anyway, let's discuss the pictures. So basically in the Euclidean case, you can see that we have that same ellipse and the blue vector, and we have a tangent here to the ellipse. Yeah, and what is the black one? So the red lines are orthogonal to one of the vectors, black. Yeah, so we have two vectors. Yeah, to measure angle, we need two vectors, right? Like blue one and black one. And to measure the angle, we need to take the orthogonal complement to the one vector and then shift it to the point where the other vector intersects the same equidistant surface, and therefore you will obtain like a projection, the projection of the blue vector on the black vector, that distance L here, and that distance L, the projection, will be the cosine of the angle between the two vectors. So, and that's how the matrix is used to measure the angles, basically. And why is that? Basically, it's because the matrix is like the generalized scalar product, and therefore those projections, they will give us the needed measurements like cosines. But actually, for the length L to be the actual cosine, you need those vectors to be of the unit length, because like if that black vector will not be the unit one, then probably I think that like you will not obtain here the cosine. You will obtain like cosine multiplied by the length of the black vector or something like that, and therefore probably I think that ellipsis here is the equidistant surface of the length 1. So to obtain cosine, we need the matrix here, which kind of cuts the unit vector into the black direction. Yeah, and for the case of the Minkowski space, we will have similar situation, but now instead of the ellipses, we will have a hyperbola there, and therefore we will do the same process. So we will take the orthogonal complement for the black vector, the tangential line to the hyperbola at the point of the intersection of the black vector and hyperbola, and afterwards we will shift that parallelly to the point of intersection of the blue vector and hyperbola, and we'll obtain that new length gamma, and that gamma will give us the probably also like the projection of the blue vector on the black one, and it will be like sorry, forgot the word, hyperbolic cosine of the angle between those two vectors. And actually that gamma factor is, or that gamma is the gamma factor required to boost one of the vectors to the other. So basically that projection will show us the gamma factor for the Lorentz transformation needed to transform like blue vector to the black one, for example. Yeah, there is also interesting picture picture, subchapter about magnitude of a form and how to measure magnitude of a form using the matrix. But there is no like really detailed information about that. So that basically says that to count it's depicted on the figure 48, and to measure the magnitude of a form, you need to simply count the number of form submanifolds inside the ellipse and divide that by 2. And in that case, the one form has magnitude 3.5. And I think that probably that ellipse should be also like a unit one, because like you need some kind of standard measurement to be happening on different forms here. So I'm kind of not sure about the size of the ellipse here, but I think that we need, like, if we are measuring the magnitudes of forms, we will need to take the same ellipses at each point to measure the magnitude there. Yeah, and that was the case for the 2 dimensions. And in 3 dimensions, like measuring the magnitude of a 2 form requires counting the number of n-2 dimensional form submanifolds inside the ellipsoid and dividing by p. And like I don't know why we have p here and 2 here, so I have no explanations here for you. Yeah, if you want to add something here, or maybe you know something about that, please give me more information. But that's kind of, yeah.
I think if it's a sphere, I mean, with the area of it would be, actually, well, I guess if it's a circle, the area of it would be pi r squared, and if r is 1, then we'd get pi. So maybe it's related to the area, and somehow with the ellipse, they're able to get rid of the like A and B, semi-major and semi-minor axis.
Yeah, it's just strange why then they don't have pi in the 2 dimensions, because it's still ellipses in 2 dimensions. And they just divide by 2 here, and that's all. So it's kind of strange for me that you have 2 in the 2-dimensional case and pi otherwise. That doesn't make any sense for me.
Could it be the number of intersections? Maybe, but like yeah.
There are 14 intersections in this picture.
Yeah, maybe.
Right.
So if you will have like a plane and sphere or ellipsoid in 3D space, then you will have like a circle intersection, right? With a pi there.
Yeah, and so that would give us 2 pi. And so if we divide that by 2, then we would just be left with pi.
Yeah, interesting. Probably that's it, yeah. We need to count intersections somehow. Okay. Anyway, I think that part is not really important for our discussion today, so let's move further to the metric dual. And metric dual is described like given a vector and then the one form, and one form is n-1 form submanifold, which is perpendicular to the vector, which we have seen in figures 44 and 45. So those were those figures with the orthogonal complement here. And in figure 49 we have like the metric dual, and what he is doing, it's like he converts a vector into a one form and vice versa. So basically it's kind of index lowering or like uppering, so index shifting operation using the matrix. And that corresponds geometrically to those pictures. So, and we have like 3 kind of vectors at ABC: space-like, time-like, and light-like vectors. And for space-like vector, which is blue here, the orientation of the one form is unchanged here, so we just taken the orthogonal complement, that's 3D space, which is right here. And for time-like vector, the orientation will be reversed. And for light-like vector, the orientation of the red form points to the direction of the nearby space-like vectors, green. So basically it seems to me that like for the light-like vectors you'll probably have it like lying inside of its orthogonal complement in Minkowski space, and the orientation will point us into the like space-like direction. Yes, so basically as far as I understand that it's also about like taking the orthogonal complement here. Okay, and then we have also Hodge Dual, and the Hodge Dual takes a P form and gives the unique n minus P form. So that's like the other kind of the duality. So like the metric dual converts vector to the form, like one vector to one form, or P vector to P form, and the Hodge. So basically it makes no difference. Like it makes the like kinda the isomorphism between the vectors and forms, and the Hodge dual it makes the connection between the P forms and n minus P forms, and in that case that n minus P form will be also like the orthogonal complement, but now for the P form surface. Yeah, and it changes the twistedness of the form, basically acts on its orientation, and in the Minkowski space, as far as I remember, that's true, that if P is even or n minus P is even, then the orientation is unchanged, and if both P and n minus P are odd, then the orientation is reversed. Yeah, and also we can see that in the case of the metric duality here, like the orientation was, like the twistedness of the orientation was preserved, and Hodge dual it changes the twistedness also of the form. So basically the orientation attached to it will change its form from like external to the internal one, and vice versa in that case. So let's take a look at the pictures here. So figure 50 here demonstrates us the notion of the Hodge dual of the untwisted forms red to the twisted forms blue in 2- and 3-dimensional Riemannian geometry. Okay, and for space-time geometry the resulting orientation may be reversed because of the matrix signatures are like different, and therefore the Levitch-Vita or volume element will have different form there. So at the picture A here we see the Hodge dual for the untwisted one form, which is red, and it becomes the twisted one form blue. So you can see that red form here has the external orientation, not internal one, and the Hodge dual, the blue line here, will have the internal orientation now, which is inside of that line. And in the case B here, we have also like the untwisted one form, which is red. You can see its external orientation here, depicted with that outer red arrow. And the Hodge dual will be perpendicular line going through it with the orientation now lying inside of it. So we convert it. And one more example in 3 dimensions. So it's a Hodge dual of the untwisted 2 form red. So we have the actual axial line here with that external circled orientation here, and to convert it to its Hodge dual, we need to take the orthogonal complement here, and then put that orientation inside. So basically it becomes the internal orientation of the plane. It just repeats the external one here. So that was the Hodge dual. Yeah, and the last theme for that chapter is about how to generate the matrix. Sorry, not matrix, measure from a metric. And basically, as far as I understand that, using the metric, we kind of can measure length, right? And therefore, imagine that you have some kind of the manifold, and therefore you can apply matrix to every point in it, and you can make you can cover with some kind of maximal precision all of the manifold using those small ellipses measured by metric. So basically you can form the manifold subdivision into those small areas measured by those ellipses, and therefore you form the measure for the surface of the manifold. And yeah, so that will generate the top form at every point of the manifold, and you will be able to integrate it and obtain the measurement of the surface or other thing on the manifold, and you can integrate that measure to give the size of any manifold, even if it's not orientable, like Möbius strip, for example. Yeah, and here it also says that this is actually the Hodge dual of the untwisted constant scalar field 1. So if you think about that a bit, scalar field and the orthogonal component to scalar will be just a part of the volume there. Yeah, so okay, I have only intuition for that part, so I probably cannot explain it to you nicely currently, but I think that the process goes something in the way I described it before. Okay, maybe you have any questions about this chapter 7 here?
I have one note about the figure 51, because there's one ellipsoid 51.
Mm-hmm.
Two ellipsoids that are not connected by their sides, but all the others are.
Uh-huh.
So is this still considered a completely packed system, or?
Yeah, but maybe you don't see the other one lying just above those, which is touching both of those ellipsoids. It just could be not drawn here.
So it doesn't matter if some of the ellipsoids are not connected. So you can,
I think they are all connected. I think they are all connected actually there. So it's kind of tight packing there. Let's think about that in small or easy examples. For example, let's take a sphere, right? And if you will try to measure length on the sphere, then the metric tensor will act. How it will act? So it will act on the tangential vectors, right? Yeah, and yeah, probably I just need to think more about that. So let's just skip that, because it is also not will not be applicable today for the Maxwell equations, for example. So that's just like some bonus information actually here. Yeah, and I think to understand that we need just to write down everything, like take a sphere, write the metric tensor, and to think about how to obtain like a volume form from it. And by obtaining the volume form, you will obtain the measure. So it's like just the twisted top form here with the positive values.
One other thing, if moving from that, one other thing I've been always pondering is how do you actually select a unit ellipsoid or any unit form? Like how do you get the unit from? It could be apparently it could be any size, but what is really the unit?
Yeah, and that's actually described in 19.4 in the Weil gauge. So, like in his theories, you can have this freedom of rescaling the matrix with some lambda constant, and therefore, like units are relative basically, and like to really obtain that unit ellipsoid, you just need to write down the matrix. And basically, it will be some kind of the like Pythagorean theorem in generalized, like x squared plus xy plus y squared, for example. And you just need to equate that with 1, and that's all. So you just equate that with 1, and you will obtain the form of the ellipses with a unit length for the current metric. But what that unit 1 means in your real system, it kind of depends.
Where do you attach the unit system?
Yeah.
So it's relational in that sense.
So yeah, actually you can have like different units, and it just will rescale the ellipsoids. It will contract those or make those bigger.
Right.
So let's go further to the smooth maps chapter here, and smooth map is just a function that maps one manifold into another smoothly. And the simplest case is diffeomorphism, and in that case we have one-to-one correspondence between the points of the source and target manifolds, and at the result the source and target manifolds will have the same dimension and same geometry, so basically they will be the same for all concepts described in sections 2.6. And by contrast, when a metric is included, the two manifolds can look very different. One example is in transformation optics, where one maps between one manifold. It's kind of I don't understand that example, so let's just skip that. Okay, so one class of smooth maps that we have encountered is that of the embedding. So embedding is a smooth map, and in this case we map a lower dimensional embedded manifold into a higher dimensional embedding. So it's basically like inclusion. And in this case, every point in the embedded submanifold corresponds to a unique point in the embedding manifold. But some points in the bigger one do not correspond to any point in the smaller one. And one more class of these smooth maps are regular projections, and they work like other way around, so they map higher dimensional manifolds to the lower dimensional, and like the whole process is reversed in that case. So, and here on figure 52 we have an example of the projection mapping that 3D manifold to the bottom 2D manifold, and you can see that those lines will be collapsed and they will be represented in the plane like a dots here. Yeah, and now we have the notion of the pullback here, and pullback, it means that we kind of, by having like two manifolds and a smooth map between those, and having a form in the target one, we can pull it back to the source one. And that's why it's called pullback. So basically we can kind of redraw form and like by having that in the target, we can pull it back to the source and obtain like a parent form there. So, and to understand that, we need to take a look at the pictures. And on pictures 53 here, on picture 53, we have a projection which maps a three-dimensional manifold onto one-dimensional, green one, and all the points on the plane, blue, they are projected to the one dot of the line. So you can think about that, that this actually 3D manifold is like a bundle with over a line with a layer which is equal to the plane. Yeah, so that's like one more example of the projection. And to demonstrate the pullback with respect to the embedding, that's so like the first examples will be about the embeddings. And here we have like pullback with respect to two-dimensional submanifold. So we have a red plane here, and it's embedded in three-dimensional space. And in three-dimensional space, we have to form those blue curves here. And to pull those back, we just need to project basically. To intersect those with the plane, and we will obtain those two green dots here, and then just to preserve the original orientation from the two form here, and therefore we will obtain a two form in a plane. Yeah, so and that's basically it. And in figure 55, we have also the pullback with respect to the two-dimensional submanifold red plane embedded in three-dimensional manifold. So we have that one form, blue planes in 3 dimensions. We intersect those with the embedded submanifold, the red plane, and we are obtaining those green lines here. And now just we are preserving the original orientation for those, and we are obtaining the one form in the red plane, which is the green lines there. So we will obtain those green surfaces. So as you can see, in the case of the embedding, we just have the intersection, and basically the forms in the higher dimensional manifolds will just intersect our embeddings, and they will give smaller dimensional forms which are the same like P forms, but in the lower dimensional world basically. Yeah, and on figure 56 we have also the pullback with respect to the one-dimensional submanifold. So we have red curve embedded in 3-dimensional space. We have one form which is blue here with that blue arrow here, and we intersect that line and obtain our green dots here, and those green dots on the line will give us the untwisted one form on the line, and the orientation is the same as the orientation of the parent form. Yeah, so basically in the case of the embedding, we just have the intersection pattern going on here. Yeah, in figure 57 we have a pullback with respect to the one-dimensional submanifold, which is red curve here, embedded in three-dimensional manifold, and the one form blue plane is tangential to the one-dimensional submanifold, and therefore the pullback will be collapsed here to 0 because like those tangential points they could not be the part of the our intersection. So basically that's the part where form equals to 0. So we do not have the correct intersection here, and that's the same situation we have had with the wedge product a few chapters ago. Yeah, and all the next examples, they're considering pullbacks, but now the other way around, and it seems to me that in this case it looks more like a pullback because you have the projections now here, and pullbacks with respect to the projections, they will look actually like a pulling back because you have, like, for example, in figure 58 here, you have smaller dimensional green plane, and you have those dots here, which are just two forms in a plane, and you kind of need to pull it back over the projection, and therefore those dots will go into the lines in the higher dimensions, and their orientation will be preserved basically and just lifted up to those lines. And actually that's like the same case depicted in the figures 59 and 60 here. So basically you kind of pull the line from a plane here to form the plane in 3 dimensions with orientation preservation, and here you pull the dot to the plane, and basically that's it. And yeah, and pullbacks while having the diffeomorphism, as far as I remember in that article, it says that it's not they are not very interesting because basically the pullback forms will be just some kind of the smooth transformation of the original ones. So basically you will just transform the surface in a smooth way, and that's all. Yeah, and on figure 61 we have the pullback of Riemannian metric onto an embedding as represented by the unit spheres. So basically, if we have the embedded plane in 3D space, we can induce the matrix on that by intersecting the 3D metric ellipses with that plane. So basically in 3D space we have those ellipsoidal forms, and the ellipses in which they will intersect that like 2D surface, they will form the metric structure on the submanifolds of the 3D space, and that's how like submetrics are formed. Yeah, and that could be done only with the embedding, actually, because with projection we don't have enough information how to lift the ellipsoidal patterns to the upper dimension, because in that direction we don't have we don't have any metric information, because it's like collapsed here and all information is lost. And we have also the dual notion for the pullbacks. It's called push forwards, and basically you can push forward the vector fields, but for push forwards they do not guarantee to be preserved, basically, and it's demonstrated on the picture below, figure 62 here. And basically if you have a line with a vector field in it, and you have that embedded into some higher dimensional space, you can push forward it to the line inside that plane, but you can see that it could be ill-defined, for example at the intersection point. So basically the nice push forwards are possible only for nice embeddings, and that's kind of the whole moral of this story here. So any questions about chapter 8? One moment, I just want to check. Do we have more people here? Okay, we have Yuri and Bradley. Hello. Yeah, okay, so at last we are at the final chapter, and probably the most interesting one here, because it will provide us like with the long-awaited geometrical intuition for the Maxwell equations. Yeah, and we have that table which describes all of the components we will need today. So basically, like, we have those described in the vector notation, their names, their form notation, and the relation between the vector and the form notation, like metric dual or Hodge dual there. Yeah, and what we have here, we have electric field, we have the displacement field, and in the previous article about forms, we also described that as electric field flux density, so it's kind of the same thing as the B, as the magnetic field here, or basically magnetic field flux density here. And because those are like flux densities, they are both two forms, but one here is twisted and the other one is untwisted here, so the interiority of the orientations will differ in that case. And for the magnetic field, we also have the magnetic field strength vector, and in the case of forms, that will be one form. Yeah, and charge density and current density, they will correspond to the 3 and 2 forms here. Okay, so yeah, we also have the table for the space-time. So in the space-time, in the 4 dimensions, we have like Faraday form F, which is 2 form, and also H form, which also will be the 2 form, and the current form, which is 3 form in 4 space, and their corresponding pullbacks are described in the column 2. So basically, if you pull back that form onto space, you will obtain the magnetic field 2 form, like magnetic flux there, and if you pull back its Hodge dual, so basically H is like Hodge dual of the F here, then you will obtain the electric flux 2 form onto space. Yeah, and if you pull the current form to the space, you will obtain like the charge density 3 form there. And the remaining components which will be left out are the corresponding electric field strands and magnetic field strands, and the current 2 form here. Okay, so basically we have like 4 main ingredients here, like E, D, B, and H, and as far as we know, those are connected by the constitutive relations, which in the vacuum are like that. So like flux equals some kind of a constant multiplied by the field strength, and that's the same situation for the magnetic field here. But as we know, in the form world, we need a way to connect like 2 forms to the 1 forms here, and for that to be done, we need to use the Hodge dual star here. So basically we are taking the Hodge duals and multiplying those by constants. Yeah, so here we will move like from electrostatics and magnetostatics forward to the magnetodynamics and electrodynamics there. So like to the electromagnetic dynamical situations. So if everything is static, then we will have like simplified Maxwell equations. Yeah, it seems that author haven't included those into the article, but he kind of writes those in the text. So one says to us that B flux is divergence free. So, and we know that means that we don't have any magnetic charges. And Gauss's law, which states that the divergence of D equals the charge, and it means that we have electric charges which kind of can pull in or like flow out the flux of the electric field from those. And we also have Faraday and Ampere's laws, which in the static case will not contain the partial derivatives over time, because for the statics they will be equal to 0. So basically it will just state that E is curl free, and Ampere's law will state that the curl of H is the current, and that's basically all. And we know that in language of forms this just corresponds, like everything of that just corresponds to the taking the exterior derivative. So basically we're just saying that dB equals 0 and dd equals R and dE equals 0 and dH equals current. So we all we have here is just the exterior derivation. Derivation. Okay, so all we have here is are only the exterior derivatives, and that's all. Okay, so let's take a look how to draw those onto pictures. So at the figure 63 we see the magnetic two-form B in 3D space, and the equality of its exterior derivative to 0 means that we have a closed form, and therefore it has no boundaries. So basically magnetic field in 3D space, which is static, yeah, it will have like D lines going on into an infinity, or lines that are self-closed, like those ellipses at the center here. Yeah, and that's like the depiction of the first Maxwell law from the article. And the divergence of the D here, which is equals R, will be depicted like that. So basically we have a 3 form, which is just like a number of points at the 3D space, and we have the thread point which is not 0, and in that case we will have 2 forms, and 2 forms are just the lines, and those lines will kind of flow into that point here, and their intersection will have some kind of the boundary there. So basically the exterior derivative of those intersected surfaces will not be equal to 0, it will be equal to R in that case. And if we'll take the Hodge dual, so in that case it means like taking the orthogonal complement to those D lines here, then we will obtain those spherical surfaces, and those spherical surfaces, they will have the exterior derivative also equals to 0, because they are closed on themselves, and therefore we will have like the other one, Maxwell equations, which tells us that curl of E equals to 0. So basically on those two pictures we have already depicted three Maxwell equations. And we need to have one more, and it's shown on the figure 65 here. It's Ampere's law, and we see that the constant line current is just the twisted two-form J, which is depicted black on the picture, and its exterior derivative should be equal to the not its, but the exterior derivative of H of the one form should be equal to that J current, and basically just means that we have a lot of those like H surfaces intersecting over that current, and therefore we will obtain something like that, like a lot of red planes self-intersecting over J here. And if we will take the Hodge Dual, you can see it depicted as the blue lines, blue circles here, and that will be exactly the flow of the magnetic field over the charged wire J. And that's the Ampere's law, and it kind of closes the discussion of the electro and magnetostatics Maxwell laws. So looks pretty simple, but actually maybe even not simple enough, because in the 4 dimensions we will have even simpler pictures. And let's take a look at those. And those 3 figures we have seen already, they will help us to form nice 4-dimensional pictures where we will have time dimension also added, and therefore the dynamical situation. And if we recall the first Einstein paper about electrodynamics, it was about like changing the reference frames, right? And changing the reference frame will kind of convert the magnetic fields to the electric fields, and that will also help us. But at first we need to start with the conservation of charge, and conservation of charge means that like exterior derivative of the current form in the space-time, it's like 3 form, right? Because like 3 form will be depicted like a lines, and currents are lines in 4 space. And the meaning of the equation that its exterior derivative equals to 0, it means that the form is closed, and therefore we will have a lot of those lines going on or circling. So that's how we depict the conservation of charge. It's just figure 67, and that's all. Yeah, I propose to skip the figure 66 because it's just about magnets and like non-vacuum constitutive relations, so basically not really important for our discussion today. Yeah, and now we have on the figure 68, what we have here is basically the our like Maxwell or Faraday tensor and twisted two-form F, and we can call that electromagnetic field, and it encodes 2 fields E and B, and since we are in 4 dimensions, the orientation is a loop outside the 2 dimension from some manifolds. So basically, like, because we are in 4 dimension, we need to have like exterior orientation assigned to that form, and exterior orientation will be 2-dimensional orientation here. So basically it's like orientation of the perpendicular surfaces to those. But question is how to understand that. So basically we have those planes in the 4 dimensions, and to understand figure 68 we need to take a look at the figure 63 here, So, and you need to imagine in that case that that if that field is dynamic and it changes over the time, then you will see like those lines moving in 3D space, and that movement will actually produce the two-dimensional surfaces in the four-dimensional space. So basically the dynamics in 3D space, which could be depicted as animation, for example, right? It could be depicted as 2D surfaces in the space-time. And that's exactly what is behind the geometrical intuition behind the Maxwell tensor. So it is actually, it depicts like magnetic field in a space-time which dynamically changes. And in this case, like we know that it could like be converted from the other perspective to the electric fields also, like by moving to other reference frames. And that's why like that, like it's some kind of the like interior product, it seems to me, you know, when you have just a line and you kind of pull it out around some kind of the vector field in the four space. And therefore like by recalling the Einstein article, we understand that that two form will contain also electric fields inside, because like by changing perspective, the magnetic field will be like could be transformed into the electric field. So that's like the intuition behind that. Yeah, and that basically that picture also tells us that like the exterior derivative of f is actually equal 0, and that just means geometrically that those surfaces, they do not intersect. They could be like self-circled somehow, and or just go to the infinity, and like that's the only possible case here. Yeah, so figure 68 is basically just the depiction of the df equals 0, and df equals 0 corresponds to the homogeneous Maxwell equation, so it depicts that the divergence of the magnetic field equals to 0, and it also depicts that the curl of the electric field also equals to 0. But yeah, and probably that also, yeah, so in that case it will also include the partial derivative of the B field. So basically we'll also have like the full-blown Maxwell equation here, where changes in the magnetic field will produce the curl of the electric field. Yeah, and the other one Maxwell equation left is the exterior derivative of the Hodge dual of our vector, of our two-form f, like d star f should be equal to the currents. And by taking a look at the pictures like 65 here or 64 here, you can notice the same pattern where we have those surfaces intersecting at the point, or surfaces intersecting by that wire. And by combining that intuition with the figure 67 here, we will have a lot of those currents going on through the space-time, like infinitely, and therefore we will have similar two forms here, which are actually Hodge duals of those forms, and they will intersect by those current flowing in the space-time. And basically that will correspond to the two other Maxwell equations, which are in homogeneous, and at that place we kind of just we were able to describe all of the Maxwell laws by using only two pictures here, and probably the also conservation of the currents. And basically that's it. Maybe you have any questions about those?
Yeah, that's really amazing. Could we go back up to the table where they describe all the forms?
Yeah.
Yeah, so the untwisted two-form F, it's like you could write it as a 4x4 matrix, and the first row and the first column only include the electric field.
Yeah.
And the other three rows and columns contain just the B field. So I really like this table 6. Yeah, I felt like, you know, obviously the images were great there, but I also felt like something clicked when I saw that the E was an untwisted 1 form, and just thinking back to like the matrix representation of F, it was really interesting to think about the pullback and the remaining component. So I just wanted to make a comment about that. I think the pictures were very informative, and it's kind of mind-blowing.
Yeah, that's true. And like by looking at those tables at first, I was a little bit confused, but after looking at the pictures, I understand something like more about those tables, and like, for example, like why that current is 3 form and we have 3 form and 2 form here. And that's like basically because we have different embedding spaces for those. Because like in 3D space, the charges will be just scalars, like just some numbers dispersed into the volumes. So just like a 3 form. And currents will be lines in 3 space, so it's 2 form. But in 4 dimensions, we will have the same currents going on, so they should be the lines, and therefore we should obtain this 3 form there. Yeah, so basically, like we have had the need in the Hodge Dual to kind of to have those like constitutive relations to work, and because those are working actually, that's why we can kind of convert like H form to the F form, because like without constitutive relations here we kind of have 2 different forms. So here we have H form, which has electric flux like distributed over space called D, and it also has magnetic field strength H over the time components. And this tensor F contains E and B, so kind of the dual case. And to connect those two, to obtain like D star F instead of DH here, we need to use like vacuum constitutive relations. And by using those, we kind of understand that that H form is kind of Hodge dual of the F form. By having like some mu 0 and epsilon 0 added. Yeah, and that's actually depicted on the figure 70 here. So you can see that we have like 2 Hodge dual forms here, and one is like closed form, and the other one is perpendicular to it, and it will have a lot of those like surfaces intersecting over the currents there. Yes, at the end of the article we also have like the depiction of the Lorentz force law, and here we have the 2 form F, which is depicted as the blue submanifold here, and we have word line of the particle, curve, the green curve here, and the force is the straight arrow red here, and the force is orthogonal to both the 2 form and the 4 velocity of the particle at that point. Yeah, so basically like force acting on the particle will be perpendicular to the forward velocity of the particle, and that to form here. And actually, I've been reading through the gravity book for that for the time of the previous week, and I saw a pretty interesting thing here, which I wanted to share with you. One moment, just don't remember the exact place, but probably it's somewhere here, a little bit. Yeah, I feel that I'm at the right place. Yeah, so here. Or maybe a little bit. Yeah. So, like, the basic idea, behind the Lorentz force law, so it could be depicted in that form, the equation 1.11 here. And here you can see the four acceleration here, so basically four force, and four force acting on the particle will be equal to the charge multiplied by the electromagnetic tensor here, which is fed with the forward velocity of the particle here. So that's like the equation of the force for the particle in the space-time, and our magnetic tensor used here to calculate the Lorentz force law. So it's basically the Lorentz force law in the space-time. And actually that equation is really similar to the equation you will obtain in the general relativity, in which we will have that Riemannian tensor of the curvature here, and we will feed to it I don't remember exactly what I'm feeding here. So basically CA here is just like a coordinate of the particle, as far as I understand. Yeah, so I don't remember the exact meanings of those vectors here, but basically that's like a curvature equation, and therefore our electromagnetic tensor could be interpreted in the terms of curvature somehow. And basically the Lorentz force law is also like a curvature or geodesic deviation analog in the case of the electromagnetism. Also, I suggest you to take a look at that book, at the gravitation book. Take a look at the beginning of the chapter 2 here, because it contains the story how we can derive the electromagnetic tensor from how we go algebraically from 3D situation to the space-time situation. And yes, or maybe I was wrong. Yeah, it was in chapter 3. Sorry, one moment.
They had a quote from Herman Weyl there as well.
Yeah, and I have skipped that. Or not. I just don't know the right page.
Well, I just noticed when you went to the
I just scrolled through. Okay, but anyway, so they have in the box 3.1, they talk one more time about measuring the basically we know that Maxwell equations is all about how particle produce the fields. So basically how particles create the electromagnetic fields around those. And Lorentz force law is about how fields act on the particle. And that's kind of the same story as matter modifies the space-time, and space-time tells matter how to move. So we have the exactly same situation, which is totally analogous to the gravitation. Maybe those will have some discrepancies later, but basically in the core they are kind of the same, and I think that's like the reason why those two were how to say, like unified by the name like classical field theories. Yeah, and after that box, which actually talks about how to measure the curvature using real particles there. So I really suggest you to read that later. And here you can see like the standard form for the Lorentz force law in 3D. And here you have a story how to convert that into the like 4-dimensional version, like where you have dp that like really bold p here over the proper time derivative, and like how to obtain the f tensor here, which is actually the electromagnetic tensor we have seen already. Yeah, so that's kind of the idea behind those. And actually in the next chapter of the book, in the 19.4, we should talk about electromagnetic potential and gauge theories. We will also talk about the curvature, and actually that's like the key, and understanding the gauge theory of the electromagnetism is the key to understanding the electromagnetic tensor as curvature. And I think that will be the task for the next year actually, and we will work on that next time. Yeah, okay, so yeah, and at the end of the article we also have interesting like slices of the space-time situation in the case where we kind of forgot one space dimension and are considering our system to be functioning like in the plane and changing there in time. Basically those two pictures could be understood from the two pictures above we have talked about before, and like the currents, they will be represented here, as you can see, as the dots instead of the lines. Well, when you remove one space dimension, and you will have the H tensor here pullbacked, and you will obtain those red lines here, and red lines will give you like H here, the flux of the electric field, and therefore like integral of flux of the electric field through the surface will be equal to the charge contained inside, and you will obtain like the analog of the Ampere law. So I think that's all for today. Maybe you have something to ask.
Did you find this article? I really like this article.
Yeah, I really like that too, and actually Pax was the one who sent it to me, so it's all like it was his how to say that, I don't know the right word, so he did the right thing.
What his finding?
Yeah. So I'm really glad, and we also have one more article from Pax, which is called like that, like demystify and gauge symmetry, and I think that we will need that to go deeper into the 19.4 of the Penrose book. Yeah, so basically that's it, and I will plan like in the next few days I will upload the recording and also plan the next call. So, and we will have call after the holidays, like on January 11th or so.